we're going to continue our heat transfer discussion. So in the last video, we've successfully gotten some form of a temperature profile for a tube like this, a typical temperature profile, and all we need to know is this Stanton number, right? All right, so we're just going to do some example calculations. Right, we have explained the importance of the Stanton number, and now we want to, calculate some temperature profile. So in our problem, we assume fully developed flow. All right, fully developed hydrodynamically fully developed, but thermally we are not so sure, right? Thermally we assume that it's not developed yet. What do I mean by thermally developing? It means that the Nusselt number changes along the tube. When it's thermally fully developed, that means that Nusselt number is constant, as H is constant. So that's important to remember. Okay, so let's give ourselves some parameters. Okay, let's try and make things simple. We'll just use water. We'll have it flowing at 0.2 meters per second. Okay, let's say it's hot water, 80 degrees C, wall temperature 30 degrees C. All right, and you have a diameter of let's say 0.5 meter, and length equals to 100 meter, for example, 100 meters. Okay, so what is the outlet temperature? Okay, so water flowing in at 0.2 meters is as a 0.5 meters. All right, so what's our Reynolds number? So we'll try to have somewhere the water density. Okay, we'll first have to find out some appropriate correlations. All right, before we we'll need to find some appropriate correlations, and that's why we are trying to find our Reynolds number. Now if you look at Paris Chemical Engineering Handbook, we can see that for flow in round tubes, we have several correlations. Okay, you can see this first one, equation 545 here. It says it's for fully developed laminar velocity profile and developing thermal profile. That's what the fully developed thing I was discussing a little earlier. So if it's laminar, we can use this. All right, so what's our Reynolds number? So we'll need density, viscosity, and the fluid velocity, which is this is the average. Now fluid velocity we have already, so let's find some density. Okay, water density at different temperature. So we're gonna just do a quick Google search. This will do. Okay. Good. We have some interesting values here. Oops. This we'll just copy and paste. Okay, so we'll quickly get some density values. and we look between, let's say, 80 and 40. We assume the temperature's around there because, well, it's between 80 and 30, so we can just assume that the average Reynolds number is, yeah, somewhere in between. It's based on the density somewhere in between. Okay, so maybe 60 degrees. Rho equals to 983.2 kg per meter cube. Okay, so this is some average. All right, so density of pure water here, 983. We'll just give it a guess. Okay, so that's density. What's the viscosity of water? Okay, at different temperature. So you can look here, somewhere like this. Okay. Yeah, this is, whoa. This is some dynamic and kinematic viscosity of water in SI units. So this is what we want. We're going to use SI units. Alright, so I'm just going to copy and paste this down here. Alright, so we see that the water actually changes viscosity by quite a bit. Almost a 50% difference between, let's say, 30 and 80. In fact, slightly more than 50% also. So we need to look for an average. Again, we'll just assume average temperature is 60 degrees C. Okay, that's just a guess. So 0.467 Newton second per meter square, and that will be our mu value. Now let's calculate the Reynolds number. Okay, so rho is 983.2, V is 0.2, D is, what is D? Is 0.5 meter, divided by mu. Okay, let's see whether this is turbulent or let's say what do you call that? Laminar flow. Okay, just gonna bring out the calculator in Excel. So 983.2 times 0.2 times 0.5 divided by 0.467. Let's go. 210. 210.53. Yeah. We see that even at the, well, even if we increase this by a factor of 2 at 80 degrees C, there's still a laminar flow. And even if we have the maximum density, 1000 kg per meter cube, yeah, about 1000 kg per meter cube, even if we go there, this is still going to be a laminar flow. Alright, so this is a good initial guess. Alright, we know we are at laminar flow, and this is a good initial guess for calculating Nusselt number. Okay, so we can try and use this Reynolds number first. It's just a kind of a guess value. Alright, so yeah, that's the Reynolds number. Alright, E D equals to 2 E D 210.53. Okay, now we'll want to calculate our Prandtl number, our average Prandtl number. So we'll need a Prandtl number, right? Okay, so we'll need a Prandtl number for our Nusselt number correlation, and then the corresponding D and L. Okay, so Prandtl number. What's the Prandtl number? Yeah, so what's the Prandtl number? Well, we will assume, yeah, we will need to find mu Cp over K. Okay, PR equals to mu Cp divided by K equals nu divided by alpha. So let's look for thermal conductivity of water. At different temperature. Alright, so this is our thermal conductivity of water. So we're going to use this table. Oops. There I scroll all over the place. Where did I point it? Yeah, there you go, 545. Okay. So that's where I get it from. And this is my Prandtl number. Okay. So this is watts per million watts per meter per Kelvin, or you just divide this by 1000, okay? Okay, so we assume about temperature. Well, the temperature we want to evaluate the Prandtl number is at 60 degrees C. Now, of course, you might be asking, am I picking this arbitrarily? Yes, I am, but there's a logic to it. All right. So we know that for thermally developing flows, the Nusselt number actually changes over the length of the tube, right? Oopsie, where is it? Let's go and find the picture of the tube. Yeah. Yeah, we know that the Nusselt number changes from here to here to here. So, which Nusselt number is this talking about? This is an average Nusselt number, right? So we actually find an average Nusselt number. But we find that this average Nusselt number is a function of the Reynolds number and the Prandtl number. So which Reynolds number and Prandtl number are we going to take? Are we going to take the REPR here, here, or here? So that's a potential point of confusion, but according to Paris Chemical Engineering Handbook, it says that the properties are evaluated at bulk mean temperature. So what does it mean? You look at the temperature that's in and the temperature that's out, and you divide it by 2. So the bulk mean temperature is the temperature here, and the temperature here, you divide it by 2. So if I assume bulk mean temperature is 60 degrees C, I assume that the exit temp is, well, equals to 60 equals to AT plus exit over 2. T exit. Alright, that means my T exit is 1. Okay, approximately 120 minus 80 equals 40. It's not too shabby an assumption, right? 40 degrees C outlet temperature. It's somewhere in between 80 and 30. That's good enough. Okay, so I'm assuming the exit temperature is 40 degrees C. That's my initial guess. So once I take the initial guess, what happens? I'm going to evaluate my Nusselt number, assuming the exit temperature is 40 degrees C. So I evaluate Reynolds number and Prandtl number at 60. Reynolds number and Prandtl number at 60. I calculate my average Nusselt number. Then I plug it into my equation. Okay, that's my equation. Yeah, plug in into this equation. Alright, I plug it into this equation. My Nusselt number, my Reynolds number, and my Prandtl number. Okay, I plug it into this equation. And then what I do is I try and find this exit temperature. If my exit temperature is somewhere around 40 degrees C, then I can accept the answer. Otherwise, I'll have to change the exit temperature and reevaluate everything again. So I'm just going to do a few rounds in this video just to get a feel of it. Okay. So what's next? We have our exit temperature, and we assume is 40 degrees C, and we assume the bulk mean temperature is 60 degrees C. All right. So bulk mean temperature is 60 degrees C. Means that this conductivity here is 0.659. So K equals to 0.659. What's the Prandtl number? Well, we still need one more property, right? Constant heat pressure, heat capacity. Heat capacity of water at different temperature. Okay, this is the last one, very important. So I can see, look at this, isobaric heat capacity. This is taken at saturation pressure, but we assume that it doesn't change. Okay, it's very constant, right? So we can just assume Cp 4180 J per kg K at all temps, just to make our life easy. Okay. Excuse me. Oh, it should be excuse me, kj per kg per k. All right, so again, let's calculate it. 4180 times mu. What's our mu value? 0.467. Yeah, anyway, excuse me. Yeah, so this is the heat capacity, this is the viscosity, this is the Kelvin, sorry, the thermal conductivity. This is million watts per millikelvin, so it's watts per Kelvin, million watts per meter per Kelvin. Okay. So the SI units should be 0.659. Okay. Joules per kg per Kelvin. Okay. Looks a bit fishy, but okay, let's try. 659 times 0.467. Prandtl number of 2000 plus. But we actually saw that our Prandtl number was about 7 for water. Yeah, so we found that our Prandtl number was excessively high. 2000 plus, which doesn't actually make sense at all. If you actually look online, well, our Prandtl number should only vary between like 13.6 all the way to 1. See, you see in this graph, it doesn't ever go to the thousands. So yeah, this is a sanity check. As an engineer, you also must always have this. So let's see where we've gone wrong. So let's look at the units. Here looks correct. Okay, look at this, dynamic viscosity times 10 to the minus 3. Okay, so it looks like we have made a mistake here. I have anyway. So this should be times 10 to the minus 3. Okay. So I put a times 10 to the minus 3 here. So yeah, the Prandtl number is about, divided by 1000, 2.962. Okay, 2.962. All right, so let's we have our Prandtl number, we have a Reynolds number. So this is the initial guess anyway. Reynolds number and a Prandtl number. And what else do we need? We need a Nusselt number. Let's go look at our Nusselt number correlation. So we'll just plug this in. All right, let's plug this in, and then we'll calculate our Stanton number. NUD equals 3.66 plus, okay, 0.668. What's the D? Our D is 0.5 meter. Our L is 100 meter. What is RED? 2.1053 times the Prandtl number, 2.962. Then the bottom is 1 plus 0.04. Okay, 0.5 divided by 100. All right, Reynolds number again, 210.53 times 2.962. So this is our first guess, 2/3. Yep. So let's get a Nusselt number. Okay, so we have a Nusselt number here. I'm just gonna use Excel to try and speed things up. All right, so the first term, numerator, denominator. Okay, what's the numerator? 0.668 times 0.5 over 100 times Reynolds number times Prandtl number. Okay, so for now 0, so the denominator is 1 plus 0.04 times, okay, 0.5 over 100 times the Reynolds number and the Prandtl number again. So this is actually the Packlet number. So I'm just going to use product of these two. And then this will be to the power of 2/3. Okay, let's put in our Reynolds and Prandtl number. 210.53, 2.962. Okay, so the Nusselt number will be this plus the numerator divided by the denominator. 5.7526. So let's check again. 0.668. Okay, I think I'm missing a 0 here. Okay, let's put another 0 here. Just make sure you copy it right. 0.0668. 0.0668 DL times the Packlet number, C5, C6 here. And the denominator, 1 plus 0.04. 1 plus 0.04. Okay. 0.5 over 100 this and this, then the Peclet number. So all this is into the power of 2 over 3. Alright, so we have a Nusselt number of 3.85, 3.851, or 3.852. Alright, so what's our Stanton number? Well, we can get Excel to do it. Okay, Stanton number. What's the Stanton number? Equals the Nusselt number divided by product of this. Okay, 0.00616117. So copy and paste it here. Text only. Okay. So the final temperature, okay, is right over. Okay, let's just substitute it. So iteration 1, this will go here. L over D. What's L? 100. Divide by D, which is 0.5. What's the initial? Fluid temperature is 80. Wall temperature is 30, so this is 50 degrees. Okay, so let's look at our final temperature. And let's just calculate this exponent. Okay, exponent equals to minus Stanton number times 4 times 100 divided by 0.5. Okay. And we'll exponential this. You'll get this. You find that the number is pretty small. Okay, I'll just paste the text better. And then we'll have a final temperature. So it's 50 times this number plus T wall, right? So it's 50 times this number plus T wall equals 50 plus, what is the number? This exponent. So it's 50 times exponent plus the wall temperature, which is 30. So you see the final temperature is very close to 30. Okay, so let's do 30.35 degrees C. Okay, so since we have a temperature very different from let's say 40 degrees C, we will need to re-evaluate. We'll need to iterate again. Okay, so what's our bulk temperature? So bulk temperature equals to, again, we divide by 2 because we have the entrance temperature and the ending temperature. Okay, so 80 plus 30.35 over 2. Okay, so our bulk temperature is about 55 degrees C. But as promised, I'm just going to go over it. Okay, so I'm going to pause now. It's going to be half an hour already. I'll see you in the next video.